This video is going to focus on differentiation from first principles, and the example we're going to use is for the equation of the line y is equal to x raised to power 3 on this line right here. So for us to be able to do this, we're going to identify 2 points along the line y is equal to x power 3. So let's say we have point A at this point, and then you have point B there. So at point A, we have the coordinates x and y, but y according to this is x power 3. So the coordinates at point A is x and x power 3. So at point B, there's going to be some increase in the value of x. So when you move from point A to B, there would be some increase or decrease in the value of x. So you're going to have x, and then let us represent that small increase using the letter h. So remember the equation says that y is given by x power 3. So it means whichever x you have, for you to get y, you just raise it to power 3. So at point B, the value of x is x plus h. So it means you're going to have x plus h, and that is raised to power 3. So the coordinates of point B is x plus h and x plus h raised to power 3. So those are the 2 points. So remember, we want to differentiate from first principles. For us to do that, we're going to use the relationship that dy dx is given by the limit as the small change in x, the one we have represented using h, as it tends to 0. So dy dx is equal to the limit as the small change in x tends to 0 of the gradient function of that line. So that is delta y over delta x. So for us to get dy dx, it means we have to first of all obtain delta y over delta x, which is basically the gradient function of this curve, and then we get the limit as h tends to 0. So the limit as h tends to 0 means that if you move A towards B, that small change in x tends to 0. For example, when you move A, B, you will find that the coordinates of A and B will be at the same point, such that there is no change in x. So it means as you move A towards B, that value, that small change in x will eventually become 0. So in the gradient function, that is delta y over delta x, any value that will, any term that will contain the small change in x will be regarded as 0 because it will become 0 eventually. Let us do that. So the first thing, let us identify the 2 points. So we have the 2 points, that is point A, and point A is given by x and y, where y is just x power 3. And then we have point B. Point B is given by x plus the small change in x. Now, for y, you have x plus h raised to power 3. So that the coordinate of B is x plus h and x plus h raised to power 3. So let us go ahead and obtain the gradient function of that line. So that is just change in y over change in x. So we are going to have x plus h power 3, that is the second y, x plus h power 3 minus y1, which is just x power 3, over change in x, which will just involve x plus h minus y1, x1, which is just x. So in the denominator, we're just going to have h, but in the numerator, for us to perform this subtraction, we have to expand this cube. So we can use any method to do this, but in this case, let us employ binomial expansion. So the power is 3, so it means from the Pascal's triangle, we are going to need row number 4. 1 plus 1, that is 2, then 1 and 1, then that is 3 and 3 and 1 and 1. So the coefficients of this expansion is 3, is 1, 3, 3, 1. And then a, in this case, that is x, will start with 3, then power 2, then power 1, and eventually power 0. And then b, which is h in this case, will be power 0, power 1, power 2, and eventually power 3. So if you multiply 1 times x power 3 times h power 0, that is just x power 3 plus 3x squared h plus 3x h squared plus h power 3. So that is this cube here. When we expand that, that is what we get. So we can now write our equation or our expression as follows. So the change in y over change in x will be x power 3, and that is x power 3 plus 3 x power 2 h plus 3x h power 2 plus h power 3, and now minus x power 3. And that was over x minus x, that is 0. So we're only left with h in the denominator. Okay, so let us simplify this expression. So in the numerator, if you try collecting like terms, you'll find that x cubed minus x cubed will be 0. So we're left with 3x squared h plus 3x h power 2 plus h power 3, and this is over h. If you look at the numerator, you will realize that there's a common factor, which is h. So just factorize so that you have 3x squared plus 3x h plus this one will be h squared, and this last one here will be h squared, and that is over h. So that h and h will cancel. So what we are left with is 3x squared plus 3xh plus h squared. But that is not what we're looking for. Remember, the relationship that we had was that for you to obtain dy dx, for you to obtain dy dx, you have to take the limit as the small change in x tends to 0 of the gradient function, that is delta y over delta x. But you have obtained delta y over delta x to be this, so it means dy dx is the limit as the small change in x tends to 0 of 3x squared plus 3xh plus h squared. So like I said, the limit as h tends to 0 means that as you move a towards b, that small change in x will eventually become 0. So this implies that along this, in this expression here, any term that is bearing h will become 0. So like this one will be 0, this one will be 0 because they contain h, which will eventually be 0. So it then means that dy dx dy dx is equal to 3x power 2. Thank you for watching.